Alright everyone, we are back and we're now doing confidence intervals for mu sub 1 minus mu sub 2. So we're looking at the difference in means of two different populations. This should have means here. Sorry, I did not catch that typo for y'all. Alright, so your conditions for constructing a confidence interval about a difference in means. You still have to prove that it's random, that they come from two independent random samples or two groups in a randomized experiment. You still, if you have sampling without replacement, you need to check the 10% condition, otherwise you don't need to. You can either do normal or large sample, either both population distributions are normal, so normal. Both sample sizes are large or greater than or equal to 30. And so you have, by the CLT, central limit theorem, you can assume that they are approximately normal. If you have an unknown shape, and we're talking about less than 30 for your n, either n1 or n sub 2. So we use a graph, so you have to plot out your different points, and you check for no strong outliers or strong skewness. Just like we did when we were constructing a confidence interval for our mu's, okay? Back in chapter 9. So you're going to use a t-test because we do not know the population's standard deviation. If they give you the population standard deviation, you can use a z-test, but otherwise you're going to use t. So it's a two-sample t interval for the difference between two means. So when the conditions are met, an approximate c% confidence interval for mu sub 1 minus mu sub 2 is the statistic plus or minus the critical value times the standard deviation of the statistic. The standard error is how it's listed on the formula sheet. Okay, here is the formula that we have, and you have to square it just like we did with our random variables. So where t star is the critical value, and remember that it will still have the degrees of freedom. Okay, so here we go. So it says, here's an example for you. Big trees, small trees, short trees, tall trees. The Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height, dBH, in centimeters. The mean of the northern half is 23.7 with a standard deviation of 17.5, and the southern half has a mean of 34.53 with a standard deviation of 14.26. So do you want to make little notes off to the side? One's going to be your northern, and you have n sub 1 is our 30 northern trees. You have a mean of 23.7 and a standard deviation from this sample of 17.5. And 2 is going to be your southern. N sub 1 is, or N sub 2, sorry, is 30 trees again. X bar sub 2. This one had a mean height of 34.53, and we are looking at S sub 2 was equal to the 14.26. So this is our different information that we got from here. Alright, so we want to construct a 90% confidence interval for the difference in the mean dBH of longleaf pines in the northern and southern halves of the Wade Cut Preserve. Alright, so we need to state, so we have mu sub 1 is going to be the true mean DBH of northern longleaf pines. Mu sub 2 is the true mean DBH of southern longleaf pines. We want to estimate mu sub 1 minus mu sub 2 at a 90% confidence level. Alright, so we have both of our populations, both of our parameters for both populations has been defined. We have said what we want to estimate, and we have given our confidence level. Okay, so now we are ready to do the plan. Now we're going to name our test, just like we do every time. We're going to do a 2-sample T interval. Okay, if you wanted to add in 4 means, you could do that. Okay, we need to check our conditions. Okay, so we have random. Say random sample of 30 longleaf pines from each half. We have the 10% condition because we are sampling without replacement. We do need to prove our 10% condition. So if you think about this, 10 times the 30 equals 300. So we will assume there are more than 300 longleaf pines on both northern and southern halves, and this works well because there was the same sample size for each. Then we need to prove normality. Okay, which this was our independence. Okay, so our normality though, so we have n sub 1 is greater than or equal to 30. Okay, so 30 is greater than or equal to 30. And n sub 2 greater than or equal to 30. So 30 is greater than or equal to 30. So by the CLT, we can assume it is approximately normal. Okay, so now that all of our conditions are met, we can now use our 2-sample T procedures. Okay, so you have your statistic plus or minus the critical value times the standard error, or the standard deviation of the statistic. Alright, so we are going to go back up to here, and we're using this as our specific formula that we're using. So you have x bar sub 1 minus x bar sub 2, because we're looking at the difference, plus or minus our t star, square root of s1 squared over n sub 1 plus s sub 2 squared over n sub 2. Alright, so now we're ready to plug in our different values. Well, first we need to find our t star, right? And so t star for 90% confidence And we have our 90%. Now, our sample size is 30, so our degrees of freedom is going to be n minus 1. So you're going to have degrees of freedom n minus 1, which is 30 minus 1, which is 29. We're looking at 90% confidence, so that means there's 5 on each side. So the area for our inverse t, we have an area of 0.95. Okay, you could also use 0.5 if you want the negative t. Okay. 1 second. We have an area of 0.95 and degrees freedom 29. And what you're going to use for your degrees of freedom, because we have two different samples, and so you're wondering maybe which n should we use, because they were both the same size, we just use 30. If there was a smaller and a larger one, you'd use the smaller n here. And if you type this in on your calculator, you'll get 1. I think it's 699. Okay. And so now we are ready to plug in our different numbers. And so your x bar sub 1 we had up here is 23.7 minus 34.53 plus or minus 1.699 square root, and I'm going to write small, 17.5 squared over 30 plus 14.26 squared over 30. And so you type that in, we get the difference here was negative 10.83 plus or minus 6.894. And so we have negative 17.724 to negative 3.936. So your question is there a difference maybe? So you can tell if there is a difference based on whether or not 0 is in the interval. Okay, so because this is not, what this is saying is that the mean, we're pretty sure that we're 90% confident that this mean here is larger than this mean. Alright, so what we're going to say is we are 90% confident that the interval from negative 17.724 to negative 3.936 captures the true mean difference in dBH between northern and southern longleaf pine trees. Okay. And if you wanted to do this on your calculator, I think I did not create enough space for this. Alright, you're going to go to menu 664. Okay. And this is not a pooled okay. You still need to do your state, your plan. And they do, you need to list your test, the degrees of freedom, and the interval. Okay? And then you still need your conclusion. So real quick, let me show you on the calculator. Alright, so if you're on your calculator, you're going to go to menu, 6, 6, 4, and we are going to use the stats that we have. So our X bar was 23.7. You had a sample or standard deviation of 17.5. We had 30 trees, and then we had 34.53. We had 14.26. We had another 30 trees here. Alright, and we get this here, and you'll notice that these are not the same numbers we got. And so the problem is that it didn't give us an opportunity to type in the confidence level we want. So if you scroll up and hit enter, you can see here that this is a 95% confidence and we want 90% confidence. And then you can see that your confidence interval should match the numbers that we got over here. Move it back here. Alright, and I think that will wrap up our confidence intervals. We will do significant tests next.